Okay, so this time I made sure my microphone turned on so I'd actually record a video. This is an overview of 11.4, what we call the comparison test. So, first I want to look at our good friend, this series of 1 over 2 to the n. So, recall this is a geometric series. One way to look at it is to factor out the 1/2 out front so that we write it as n minus 1, right? When you pull one of the twos out, you have n minus 1 left inside, and now that fits the description where a is 1/2 and the common ratio is the 1/2 as well. So our formula says this converges to a over 1 minus r, so 1/2 over 1 minus 1/2. Well, 1 minus 1/2, 2 over 2 minus 1 over 2 is 1 over 2. 1/2 divided by 1/2 is just 1. So as we kind of saw before, many arguments we can use to say that this series converges to 1. Right? Okay. So the big idea that I'm trying to emphasize right now is just that this converges. Even more so, converges to 1. Well, compare this 1 over 2 to the n plus 1 with 1 over 2 to the n. Because this denominator is larger than this one, dividing by something larger will result in something smaller. So 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n, which means that adding up all those terms together will still be smaller than adding up all of these terms. So the series where we go from 1 to infinity is going to be less than the series where we go from 1 to infinity because each nth term is smaller. So each an is less than, let's call them bn. Well, we already figured out actually that that term on the right-hand side converges to 1. So I know that this series must converge as well because it is less than 1. Now, this doesn't necessarily tell us what it must converge to, but we at least now know that it converges, which, as we kind of emphasized with the last section, a lot of the time that's kind of where we stop looking. Once we know it converges, we're typically pretty satisfied with that. So let's give this a name. We call this the direct comparison test. Now in this case it converged because we could see that it was small enough. So let's write that out. This direct comparison test gets 2 pieces. If one sum is convergent, and the terms from another sum are smaller, then the sum with a smaller term is convergent as well. Well, now imagine the same situation, or a similar situation, but if I told you that, well, Bn is divergent and the b terms are larger than the a terms, then that an series is divergent as well. Now, this actually turns out greater than or equal to, less than or equal to, but oftentimes the or equal to part doesn't come up, so we don't look at that as much. But we actually do need an extra stipulation that we want all of the terms to be positive. Once we start considering some negative terms, some really interesting and weird things can happen. But again, we're focusing on just positive series for the immediate time. So we can ask the question, does, I'll zoom in to look at this, something like 5 over 2 to the n squared plus 4n plus 3 converge? Well, this problem looks a little messy. Do we want to use the integral test exactly on this as it's written? Probably not. But this polynomial is larger than this polynomial in the denominators, right? Which means that the fraction is smaller. So if this would converge, then I know this one must as well. So if we take this integral, 5 2x squared from 1 to infinity, I can pull the 5's half out front so that I don't have to think about it right now. 1 over x squared, add 1 to the power, divide by the new power, evaluate from infinity to 1, 5 halves times the limit as a goes to infinity, negative 1 over a minus 5 halves, negative 1 over 1. As a goes to infinity, 1 over a goes to 0, negative, subtracting a negative turns into a positive, so positive 5 halves. So the integral converges. That tells us that the series does as well. 5 over 2 to the n converges. So the series with smaller terms that we started with in this question converges as well. Okay, so practically speaking, that's how this comparison test works. We see something that maybe we don't really want to use the integral test with, or maybe it doesn't look geometric enough, but we can compare it with something that we do understand, something we do have the integral test easily for, and we can find that, determine if that converges, and make the same claim. Now, one thing that we can do, let's consider, that was, so far we've just kind of looked at examples that converge. What about diverging? What about this one? Using k's instead of n's for no real reason. Do we know anything about this? Well, the natural log is going to be greater than 1 once we're past 3. Right, the natural log of 1 is 0. The natural log of 2 is something less than 1. The natural log of 3 is actually going to be greater than 1. So multiplying by the natural log of k, as long as k is greater than 3, is actually going to make this larger than this. So going from 3 to infinity, this is going to be a larger sum than just 1 over k. But again, we don't care about the front finite terms. This is still going to diverge. So because we're greater than something that already diverges, the comparison test tells us that this going from 3 to infinity diverges as well. And sure, add a couple of finite terms back into there. Infinity plus a finite number is still going to be infinity. So going from 1 to infinity, we are still going to diverge. So if we find something that is smaller than us, that diverges, then we diverge. If we find something larger than us that converges, then we must converge. So that's all the direct comparison test really says. And practically speaking, that's all that we really do. Look at it, see if we can look at a nicer thing that we understand the behavior of. If that greater term diverges, then if the smaller terms diverge, then we diverge. If the greater terms converge, then we must converge. Now, it doesn't tell us anything if AN diverges and BN is smaller than AN. Then we don't know about the sum of Bn. Because all we're saying is that this sum is smaller than something that goes off to infinity, which still means we could just be infinity minus 1 or something like that, right? Which is still infinity, right? So we're not actually making progress if we find something larger that diverges or something smaller that converges. It's going to be the same kind of problem. We specifically want to bound ourselves somehow, and that's what this section is kind of looking at. Okay. Next we have what is called the limit comparison test. This one is actually really interesting. So suppose AN and BN are positive. Once again, if we take a limit as n goes to infinity of AN over BN, and we get a finite number C that is positive, which again, it should be positive if it exists at all, because these are two positive things, right? Then either both series converge or both series diverge, which means they have the same behavior. Now, this means, well, this is a really big idea. We can call this like asymptotic to each other. There's notation about what this means for like other scenarios, because different topics of math like really love this idea. But for us, this is actually really neat and really useful for this specific case. So we're not going to give it the full-on name for two series to have this comparison like this, but it is really cool. Okay. So let's look at that same example from before, 1 over 2 to the n, but let's make it minus 1. Now those terms are going to be slightly larger than 1 over 2 to the n. Right? Subtracting 1 in that denominator is going to give you a slightly smaller number, which is going to give you a larger fraction, right? 2 over 3 is smaller than 2 over 2. By subtracting 1, you get a larger fraction, right? Subtracting 1 in the denominator gives you a larger result. So this comparison test would end up failing from before, the direct comparison test, because this is going to be a greater series than this one. So this one converging doesn't tell us anything about what's happening here. So this motivates maybe a different kind of limit test, and that's exactly what we're going to see here. So let's do the limit comparison test, and do the limit as n goes to infinity of an over bn. Now it doesn't really matter which one is a or b, it's just going to give you either c or 1 over c. This looks like 1 over 2 to the n minus 1 over 1 over 2 to the n. Now if you do keep, change, flip, this is going to turn into 2 to the n over 2 to the n minus 1 multiplied by the reciprocal, right? Now, what we're looking at here is actually something really, really straightforward. Sure, you could use L'Hopital's if you want, but that's not probably going to help us too much. Well, actually, yeah, I guess it could. Yeah, sure, let's use L'Hopital's, why not? That'd be 2 to the n times the natural log of 2 over 2 to the n times the natural log of 2. The derivative of negative 1 turns to 0. So all we're left with is 2 to the n times the natural log of 2 over 2 to the n times the natural log of 2, and that's just 1. So, all things considered, this limit is just 1, which means our limit comparison test kicks in and says that either both converge or both diverge. But we already know this one converges. So must this one. Because they're asymptotic, that's the word. The limit comparison test says that they have a finite ratio with this limit. That means that the two series have the same behavior. One converges, the other one does as well. So that's the idea here. Not only, like with the direct comparison test, do we have to find one that's strictly a nicer series that's strictly greater than or strictly less than based on what we think is happening. We just find one that we do understand and we think we can do this limit. Then, as long as we get a finite result for this limit, then they have the same behavior. So even more kind of straightforward than the direct comparison test. The direct comparison test should stick out if it seems obvious, but if you're not quite sure which direction you should go, then as long as the terms seem like something nice would cancel out division-wise, go ahead and go for the limit comparison test.